Hey guys, my name is Michelle and the person writing is Darren. And today we're going to teach you guys about atoms. So atoms are the smallest unit of matter and they're also indivisible, which means that they cannot be divided. So this is what an atom looks like. As you can see, there are subatomic particles in the middle here, 4 of them, and there are 2 on the outside. By the way, subatomic particles are only components of the atom, and that's why they're not considered units of matter. There are 3 types of subatomic particles. The first is the proton, the second is the neutron, and the last one is the electron. Protons are the positively charged subatomic particles. This was proven through Rutherford's gold foil experiment. In his experiment, Rutherford took a good gold foil and then he shot alpha particles directly at it. And he looked at how the alpha particles reacted. As you can see from the diagram, when the alpha particles came close to the gold nucleus, they deflected. When they didn't have any contact whatsoever, they were unaffected, but when they had direct contact, they deflected back to where they came from. Neutrons are neutrally charged, and electrons are negatively charged. The proton and the electron are equal in an atom. When they are different, however, in an atom, that means that they are ions and they will have a charge.
An ion's notation is usually seen as like this. For example, calcium. Calcium, it has a 2+ charge, and so Ca is the element and 2+ is the charge.
The mass of these subatomic particles are measured in AMU, which is atomic mass unit. So the proton and neutron both have 1 AMU. While the electron has 1 per 1,836 AMU, which means that it's the smallest of the subatomic particles. As you can see in the diagram, the proton and the neutron are located in the nucleus, while the electron orbits outside of it. The biggest number that's in the middle, A in this case, is the element, while the top number, X, is the relative atomic mass. Z, the bottom number, is the proton number. The proton number is the number of protons that the element has, while the relative atomic mass is the sum of the protons and the neutrons in that element. Take oxygen, for example. It has a relative atomic mass of 16 and a proton number of 8. So the number of protons is 8, the number of electrons is 8, and the number of neutrons is also 8.
But what about chlorine? Why does it have a relative atomic mass of 35.45? How is that possible?
Isotopes are elements that have the same number of protons and electrons, but different number of neutrons. An example of this is chlorine. It can have a relative atomic mass of 35 or 37. To find out different relative atomic masses of an element, we use an instrument called the mass spectrometer. The mass spectrometer has 5 different stages: vaporization, ionization, acceleration, difflection, and finally detection. Stage 1, vaporization, is when the sample is injected into the instrument where it is heated and vaporized, producing gaseous atoms or molecules. Oh no! Next, ionization is when the gaseous atoms are bombarded by high-energy electrons, which generate positively charged species. Acceleration is when the positive ions are attracted to negatively charged plates and are accelerated in the electric field. Stage 4, deflection, is when the positive ions are deflected by a magnetic field perpendicular to their path. The degree of deflection depends on the mass-to-charge ratio. The species with the smallest mass and the highest charge will be deflected the most. Lastly, detection is when the detector detects species of a particular mass-to-charge ratio. The ions hit the counter and an electrical signal is generated.
After the process, the mass spectrometer will show the results in a graph of relative abundance against atomic mass, which looks like this. From this graph, we can find the relative atomic mass of the element by calculation, and it's very simple. So, using my previous example, there will be chlorine 35 and chlorine 37 with these abundances. And how do we calculate them? Well, first, it's as simple as 1, 2, 3. You just multiply the atomic mass by the percentage and then add it with the abundance multiplied by the percentage of the isotope. From there, you will get 35.45, which is the relative atomic mass of chlorine. Other than for calculation of relative atomic mass, isotopes have many uses. Iodine 125 and 131, for example, are used as tracers in medicine for treating and diagnosing illnesses. Cobalt-60 is used in radiotherapy. And lastly, carbon-14 is used for archaeological dating, or more commonly known as carbon dating. This concludes the first part of the 3-part video about atomic structure.